So, picture this. A million users hit your site all at once. It's the traffic spike you've been dreaming of. And then boom, alerts start screaming. Your Redis cache is missing everything and your database is just melting under the load. We're going to break down exactly how this nightmare happens and, more importantly, how you can build a caching strategy that's a fortress, not a ticking time bomb. Right, this is the million-dollar question, isn't it? Every single developer runs into this the second their application starts to scale. It's not just about having a cache, it's about using it in a way that doesn't actually become the single point of failure that brings the whole system down. On the surface, the logic feels so simple. Check the cache. If the data's there, perfect. Return it. If not, no big deal. Just go to the database, grab what you need, and stick it in the cache for the next time. It's just common sense. And look, for a small app, this works just fine. But is it enough when things get serious? The short answer? Absolutely not. Now, let's add the one thing that changes the entire game: scale. We are not talking about a few hundred users here and there. We're talking about a million simultaneous requests hitting you all at once. And this is where that simple, common sense logic starts to completely fall apart. At this level, every little architectural choice gets magnified, and a tiny flaw can turn into a catastrophic failure, like instantly. And this is the trigger: a simple cache mess. Under normal load, who cares? It's a tiny performance hiccup. But when a million requests all have a cache miss at the exact same moment for the exact same reason, well, that's not a hiccup anymore. That's a stampede, and it's heading straight for your database. And this is the crucial thing to understand. At scale, it's almost never a simple bug in your code that takes you down. It's an architectural flaw. And a bad caching design, that is one of the most common silent killers in any tech stack. All right, let's get into the specifics. Problem number one is called cache penetration. And honestly, it's like launching a denial of service attack on yourself. So, what exactly is it? Cache penetration happens when requests keep coming in for data that just plain doesn't exist. Think about a request for something like user ID equals -1, or maybe a maliciously crafted random ID. Because this key is not in your database, it will never be in your cache. And this shows the deadly loop it creates. A request for a bad key comes in. The cache goes, nope, don't have it. So the request moves on to the database. The database does a whole search and comes back with, nope, don't have that either. And here's the critical part: nothing gets written back to the cache. So when the next request for that same bad key arrives, the whole expensive cycle just starts all over again. Now multiply that by thousands of automated requests, and yeah, your database is toast. Okay, let's move on to our second failure mode, which is maybe even more common. We call this the hot key problem. Just imagine you have one piece of data that's incredibly popular, a viral article, a best-selling product. It's sitting there safely in your cache, serving millions of requests. But what happens the very second that it expires? This right here is cache breakdown. That one super popular key expires, and in the exact same microsecond, thousands, maybe millions of requests that were hitting the cache suddenly bypass it and slam into your database, all asking for the very same thing. It's often called a sundering herd, and it can easily crush a database that was only ever expecting to handle a few requests at a time for that particular piece of data. So, if just one hotkey can cause a thundering herd, what do you think happens when a whole bunch of popular keys expire at the exact same time? Well, that's when you get a cache avalanche. This usually happens when you do something that seems really sensible, like warming up your cache by loading a bunch of data when your application starts. If you give all those keys the same time to live, or TTL, well, you're basically setting a time bomb in your own system without even realizing it. Just look at this timeline. At noon, you cache a whole set of keys, all with a 60-minute expiration. For 59 minutes and 59 seconds, everything is running perfectly. Your cache is taking all the heat. But at exactly 1 p.m., they all expire together. All of them. Suddenly, every single request for any of those keys results in a cache miss and a direct query to your database. The query volume just goes through the roof and the system collapses. Okay, so we've just met the three horsemen of the cache apocalypse: penetration, breakdown, and avalanche. And yeah, it sounds pretty grim, but the good news is that for each of these failure modes, there are proven, battle-tested defensive strategies. So it's time to build our fortress. First up, how do we stop cache penetration? Well, the simplest fix is to just cache the not found result. When your database says a key doesn't exist, just store that null result in Redis for a few minutes. Problem solved. But for a more robust solution, you can use something called a Bloom filter.
It's this really clever data structure that can tell you if an item is definitely not in your database, letting you block most of those invalid requests before they even get a chance to hit your cache. Now for that hotkey problem. The best tool here is a distributed lock, like a mutex. Think of it like a single-person gate at a concert. When that hotkey expires, only the very first request gets the lock and is allowed to go fetch new data from the database. All the other thousands of requests, they just have to wait a moment. This way, only one query hits your database, and you completely prevent that stampede. And finally, to prevent the avalanche, the idea is actually pretty simple. Just don't let everything expire at the same time. You need to break up that synchronized expiry. Instead of having a single point of failure, you can stagger your TTLs, you can implement rate limiting to control the flow to the database, or even build your system to gracefully degrade. Because believe me, serving slightly stale data for a few seconds is way, way better than your entire site crashing. And here's a pro tip. A really simple and super effective way to stagger those TTLs is to add what we call jitter. And it's literally one line of code. Instead of a fixed expiration time, you set it to your base TTL plus a small random amount of time. This tiny change ensures that your keys expire gradually over a window of time, which smooths out the load on your database and completely prevents that avalanche. So let's just recap the difference here. On one side, you've got the fragile system, the one that's going to crash. It allows unchecked keys, it has synchronized expiries, and it uses identical TTLs. On the other side, you have the resilient, safe system. It uses Bloom filters to block bad requests, distributed locks to manage hotkeys, and staggered, jittered TTLs to prevent avalanches. You know, after looking at all these different ways a cache can fail, it really leads us to a fundamental shift in how we should be thinking about caching in the first place. It's so easy to get caught up in the performance numbers and the speed, but there's a much deeper purpose at play here. And this is the most important takeaway of all. We always think of a cache as a tool to make our application faster. And yeah, it does that. But at scale, its most critical job is to act as a shield, a protective barrier for your database. It's there to absorb the spikes, to handle the failures, and to make sure the core of your system stays online no matter what. So the next time you design a caching layer, don't just ask, how can this make it faster? Instead, you should be asking, how can this make my